Welcome everyone to the fourth video of this COA lecture series. In today's video, we're going to learn probably the most important topic in your course, that is the Booth's algorithm. It is a landmark in this subject because after this so many multiplications and other operations became so easy. That's why I've made this whole video on this Booth's algorithm, that what used to happen before this algorithm comes and then what happens after this. This is a very important question in your exam, probably a 10-mark question, that what is Booth's algorithm and an example of it. It's very important, and if you know this like appropriately, you will score 10 on 10. It's super easy also, but you need to make all the concepts very clear. It will be a long video, so I am requesting you all to listen carefully and please watch this video till the end. So let us start. Before landing in these main topics, I always believe in clearing your basics. So the first question that comes to my mind when I saw this is, what is a multiplication? Okay, the answer is repetitive addition. Why? Suppose I have taken the example of 2 cross 3, right? So we know 2 cross 3 means that you need to add 2 3 times, or you can add 3 2 times. Okay, suppose I have done this here. 2 into 3, it means 2 plus 2 plus 2. So 2 plus 2 is 0 1 0 0. Then the next step 0 0 1 0, it's 0 1 1 0 6. But you can see that just to multiply 2 cross 3, I have to done so many steps here. Like, so suppose 15 cross 15, it means 15 plus 15 plus 15, till 15 times I have to add 15, right? So just to do this small operation, so many steps are required, and it also increase your time. I think when you're gonna learn algorithms properly, you can understand that the time required for this will be on like exponential form. So that is why we need multiplication. In multiplication, it reduced the number of steps and also the time, right? So this is why multiplication is needed. Okay, say for example, we have taken this 5 cross 3. Now 5 cross 3, it means 5 plus 5 plus 5 plus 5 plus 5. So we had to add 5 so many times. But we can see that with the help of multiplication, we can perform it in quite a few steps, and it is quite appropriate too. I mean, it's completely appropriate. Okay. Now, I want you to notice something, that when we are multiplying two numbers, I mean to multiply, obviously you need at least 2 numbers. So the first number is called multiplicand. So the first number is multiplicand, and the second number is the multiplier. Okay. 5 cross 3, first one is multiplicand, second one is multiplier. We know that the answer will be 15. So the 15, the result, it is called the product. Now 5 cross 3, 5 can be represented with the help of these 4 bits, 1 0 1 0, and 3 is 1 1 0 0. I think we all remember that we used to do these kind of multiplications when we used to go to school. So it is super easy. It's same like that. It also works in binary too. Notice something. There are 4 bits. So okay, just do this with me please. 1 1 0 0. So 1 multiplied by this, it will be 1 0 1 0. Again it's a 1. We know that there is a shift. So 1 is 1 0 1 0. Then there is 0 0. So we can just do the shifts and put 0 everywhere. After that, we just add all these 4 combinations, or what should I say? number of bits presented in the multiplier equals to the number of steps required to perform the production. Okay. Now these are called as partial products. Please remember this one. It's very important to remember. I think you will understand the importance of these terms later. Now the points to remember is number of bits in multiplier equals to the number of steps required for multiplication. Okay. So in this page the most important topics are what is multiplicand and multiplier. I think you are now quite familiar with this. So just move on to the next page. Multiplicand or the first number and multiplier or the second number, they are represented as M and Q. Okay. As you can see that when the multiplier is 1, we just write the bit as it is the multiplicand. So we have taken the same example here also. If it is 1, then the multiplicand remains same, right? We just write the multiplicand. And when the multiplicand is 0, we put 0 everywhere, right? So now just answer me a question that is there everywhere we are doing some kind of multiplication? No. We are just accumulate all the bits here. That is why here we need a register called accumulator. Okay. So point to remember, if Q is 1, then write it as the M means multiplicand, right? And if not, then put 0 everywhere. But the most important topic is don't forget to do the shifting. Okay. So if it is 1, then write 1. If it is 0, then shift and then write 0. So we are not actually doing any kind of multiplication here. What we are doing is accumulate all the bits and then add them. This is why we need an adder. I will try to make a separate video on the adder part because it's really important to know what its function is. But for now, please just notice to my words. That's it. Now the more important point you need to remember is number of bits presented in the multiplier and the number of bits presented in the multiplicand equals to the number of bits in the product. Okay. Say for example, if I take a 2-bit number, we know that 2-bit number can give us 4 combinations, right? Suppose the 1 and 0, right? That the 2-bit numbers, they can give us 0, 1, 1, 1, 0, 0 or 1, 0, 4 combinations. So suppose I have taken a 2-bit number and then I have taken also a 2-bit number. 2 into 2 equals to 2 to the power 4. So we get 16 combinations. So always remember that the number of bits presented in the multiplicand and the number of bits presented in the multiplier equals to the number of bits presented in the product. Like if we take 4-bit multiplicand and 4-bit multiplier, the result will also, it can be in 4, 7 bits or on, but it will not be more than 8 bits. Okay. So suppose I have here comes as a 7-bit. If we write a 0 here, it doesn't make any difference, right? So don't forget that the number of bits in the multiplier plus the number of bits presented in the multiplicand equals to the number of bits presented in the product. The number of bits presented in the product may not be the same as it is, but it will never greater than this one. It will maybe lesser than this one, but not greater. I've also made you a proof. So if we follow this example, how it is done, I want you to show in via some steps. So I've already told you what the accumulator is doing here. We have just accumulate all the bits, right? That's why we are using an accumulator. Now I've told you that there will be a sum about the bits. So as I've taken 4 bits here, so I'm taking a 8-bit multiplicator, 8-bit accumulator. Because the M is also about 4 bits and the Q is also of 4 bits. 4 plus 4 equals to 8 bits. So the accumulator is of 8 bits. Now, the next step, I told you that check whether the Q is 1 or 0. Okay. So, if we just see this example that the Q is 1. So, add first, okay, sorry, I want to mention this. First, clear the accumulator or initialize it with all zeros. So, if there is an 8-bit accumulator, then there will be all zeros. And now, what is the next step? Check if it is 1 or 0. I mean, the multiplier is 1 or 0. Here we can see that it is 1. And what is the multiplicand? 0, 1, 0, 1. So, what we have to do? A plus M. Accumulator and the multiplicand will be added. Now, we can see that we always do the shift from right to left. But here, we have to add the bit at its extreme left. So 0, 0, 0, 0, 0, 0, 0, 0, the accumulator, and the multiplier is 0, 1, 0, 1. So add them 0, 1, 0, 1, and the rest is 0, 0, 0, 0, right? What is the next step? We have to make a right shift, right? See this one. 0, 1, 0, 1 and 0, 0, 0, 0 was a result. We have to do a right shift, and it is, so suppose this will come there, this will come here, this, 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 and there will be a, in this vacuum place we put a 0 as we do here. Like, what did you put here, right? We always have zeros here. So it is easy for us to calculate. At same, so we do a right shift and put zeros there. So 4-bit multiplier, it means it took us 4 steps. So it's a step 1. Next step, again check whether it is 1 or 0. It is 1. So what we have to do? Accumulator plus multiplier and then a right shift. So 0, 0, 1, 0 and 1, 0, 0, 0 was your result. Now add 0, 1, 0, 1, 0, 0, 0, 0. It is 0, 1, 1, 1, 1, 0, 0, 0. Then do a right shift, okay? So it is, if we do the right shift, it will come to here, here, there. As we know, I think we all know right shifting, okay? So there was a 0 which comes to there. So the vacuum place is also again 0. So step 1, step 2, now step 3 and step 4. I've, here I have done this in these initial steps. I want you to do this, but I've practiced them a lot, so I can retain them directly, but I'm requesting you to do it at your own. You can see that the next 2 bits are 0, 0. So if we do A plus 0, it will remain same, right? A. But the right shift is the most important part. So I'm not adding the zeros anymore to, like, I don't want to waste paper. So we are not adding zeros anymore. The only thing that we are doing is the right shift. So this was your result, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0. After a right shift, it will be 0, 0, 0, 1, 1, 1, 1, 0. Okay, this 0 will be eliminated. On the next step again, and this 0 comes to here. So 0, 0, 0, 0, 1, 1, 1, 1. This is your product. And what it is? 1, 2, 4, 8, 15. 3 cross 5 equals to 15, right? This is right. So what we can say from this entire lecture, that 4-bit register for multiplicand, a 4-bit register for multiplier. Hence we need a 4 plus 4 equals to 8-bit register for the accumulator. From now I will write ACC in spite of accumulator. Please try to understand this. Now these steps, I want you to draw a diagram and make them more clear to you. But first listen to what I am saying, then ask questions. As we can see that I have drawn a 4-bit register for multiplicand, a 4-bit register for multiplier, and a 4-bit register for accumulator. Here comes the parallel adder, and there is the control unit, and this is the XOR gate. Now let me discuss all the points. Obviously, I'm sure that you guys are like questioning me that why there is a 4-bit accumulator. Just a second before you told us that there will be an 8-bit register. Then why we are using only 4 bits here? Okay, I will answer this question gradually. Just do the steps with me. Please follow all the steps that I'm saying. Okay, this was the product that we need to perform. What we are doing, I'm repeating all the steps to make you understand that what is happening inside the computer. Step 1, check whether the multiplier is 1 or not. So multiplier sends a signal to the control unit. Then the control unit decides that whether the multiplier, according to the bits of the multiplier, that whether the accumulator and multiplicand will be added or is there will be any changes and so on. I will tell you later. So first step, 1 will come. So control unit understands that now we need to add the multiplicand with the accumulator. I know maybe this XOR gate is bothering you, but let me tell you that inside the computer, while we are doing multiplication, it's not the addition that we have to do all the time. Sometimes we all have to subtract 2. And you know that suppose I have 5 minus 3 equals to 2, right? But if we do 5 plus 2's complement, it will give me the same answer. I'm pretty sure that you know, because I have made an entire video about this topic, that how minus the negative numbers can be translated in 2's complement and make a whole new number. So please don't mess up. A minus m or a plus m's 2's complement gives the same result. That is why the XOR gate is needed. But now we are not using the subtraction, so please avoid this one and just listen to what I'm saying. 1 is coming, so control C unit says that okay, just add a plus m and do a right shift. So the first one, add a plus m. So if we add 0, 0, 0 plus 0, 1, 0, 1, it will give us 0, 1, 0, 1, right? Then what we have to do? A right shift, right? If we do a right shift, it will be 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, and this one will get eliminated. That's right, and there will be a 0. This is why we are not using a 8-bit accumulator, because each time when we do a right shift, 1 bit is eliminated directly from the multiplier. Hence 8-bit accumulator is not needed, because each step deletes 1 multiplier, then second, then third and fourth. What we need in the multiplier is the LSB, right? We just need to check the LSB that whether it is 1 or 0. The rest of the bits, they are not they're not needed while we are doing the operations. This is why, and then after the whole 4 bits are deleted from the multiplier itself, the result will come in the whole accumulator and the multiplier. These 4-bit register and these 4-bit register, they both will give us the combinations of the answer. Okay, so step 1 is 0, 0, 1, 0. Next step, again there is a 1. So what we have to do? A plus m, then do a right shift. Okay, there's not so many space, so I'm doing this here. 0, 0, 1, 0 plus 0, 1, 0, 1. Guys, please do this with me, otherwise you will get confused a lot. So 0, 0, 0, 1, 1, 1. After a right shift, what it will be? 0, 0, 1, 1, right? So cut this 0, 0, 1, 1. The 1 will come here. 1, 1, 0, 0. Right? For the next 2 steps, there is 0, 0. So when multiplier sends the signal to the control unit that there is a 0, then the control unit understands that there is no addition, so there is no change. We just have to do a right shift. So 0, 0, 1, 1. First right shift will give you 0, 0, 1, 1, 1, 1, 0. And the second right shift will give you 0, 0, 0, 0, 1, 1, 1, 1. So the final answer is 0 0 0 0 1 1 1 1. So as you can see, when we are using a 8-bit accumulator, or whether we are using the accumulator and the multiplier both, the result is same. That is the 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1. I hope you understand. So this is why we use the multiplier and accumulator both as one register to produce the product. I hope you are sure and you are pretty much clear about it now. Next. Okay, here comes some tricky. 5 into minus 3. Here comes the sign number. Sign number can be positive and either negative too. 5 plus 3 should give you minus 15. Okay, so minus 15 plus 15 is 0 0 0 0 1 1 1 1. So minus 15, it will be its 2's complement, and that is 1 0 0 0 1 1 1 1. Now see, we follow the same procedure that you used to learn in school, what will be the result? So I have already done this. Please do this yourself. The result is 0 1 0 0 0 0 and whatever. They are not same. It's a positive number, it's a negative number. So this procedure doesn't apply for sign numbers. It can't perform multiplication on sign numbers. Now just say me one thing. Do you wanna perform multiplication the rest of your life by just doing this by doing this positive number multiplications? Obviously not. We need to perform on sign numbers. This is why then the concept of Booth's algorithm comes. So this procedure fails where it can't perform sign number. I know my handwriting is a little bit bad. Please try to understand this. So it can't happen when it comes to sign number multiplications. So guys, be careful. Now we will learn Booth's algorithm. Do you know what is algorithm? Okay, let me tell you. Suppose you bought 2 packets of Maggi, and then you have to cook it and then have to serve this to eat. So we take 2 Maggies, then we take a bowl, then we used to give water into it, then boil it, then put the Maggi, and after that we have to boil them for 3 minutes as Maggi demands and all, and then we serve the Maggi. So the procedure of cooking is algorithm, but obviously it is not cooking. Algorithm is a mathematical procedure, so step by step mathematical procedure. We can take some inputs. After the mathematical procedure, we have this output. This step is called the algorithms. Now comes to Booth's algorithm. It's a huge topic. But before I started Booth's algorithm, I have to give you examples of Booth's algorithm, otherwise you will not understand. But I obviously want you to do something, that is, be very clear about the number of bits, write the numbers in both positive and negatives. And here also, the number of bits in a multiply equals to the number of steps required to perform the production. Now, when I say that be very clear about the bits, listen to my words very carefully. If I take a 5-bit multiplier and if I take a 4-bit multiplicand, it might give me some wrong results. So try to keep them equal. So if to not take a 5-bit register, maybe the size of the register will increase, but you will get the correct answer. Okay. Before I start the Booth's algorithm, guys, be very patient. From now, just give me 10 minutes. I will clear all your doubts, but listen very carefully. Be very clear about the bits. Write the numbers in both positive and negative. The number of bits in the multiply equals to the number of steps required to perform production. Now come to the main topic. 4 cross 6. I have taken this example. We know the first number is called the multiplicand M and the second number is the multiplier. So I have written both in the forms plus 4 minus 4 plus 6 minus 6. We know that 4 cross 6 equals to 24. I have already written so that I can check after my each operation. Okay, now listen to my words very carefully. Here's the multiplicand M4. I will say what it is. This is multiplier 6 and then the accumulator. Let us start. Step 1. Check the imaginary bit with the LSB. Whether it is 0 to 1, 1 to 0 or 1 to 1 or 0 to 0. As we can see here, it is 0 to 0. When there is 0 to 0, there should be no operations, only a right shift. I think now it is a high time to tell you guys that why the procedure that we used to follow fails when it comes to signed multiplication. Just give me a second. See this one very carefully. We know that if it is plus 5, it means 1, 2, 4, 8, 1, 1, 0, 0. We can put numerous zeros before them because it is a positive number, right? But when it is a negative number, then there will be infinite numbers of ones before them. When we do this operation, we always assume that there are zeros in these vacant places. See this one, and then we add them. But we can say, suppose minus 5 will give you minus 10. It will not give you plus 10. So if we assume it as plus 10, then your whole operations become wrong. This is why as we are assuming zeros here, the operations on signed numbers become fail. This is why we need to use Booth's algorithm, where on every right shift, suppose, okay, let me show this again. Suppose there is a 8-bit register, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, sorry, 4, 5, 6, 7, 8. 1, 0, 1, 1, 0, 0, 1, 1. After a right shift, what will be the answer? 1, 0, 1, 1, 0, 0, 1. What we will get in this vacuum place? We know that the MSB decides that whether the number is a positive one or a negative one. So this is the most significant bit. Okay, good. We are right that we have to put the bit 0 or 1 with the respect of the bit that is placed on later. What it is, I mean, I may sound a little bit tricky, but please listen to my next word. You will get a clear view. If it is 1, then you have to place 1 there. If it was 0, then you have to place 0 here. Okay, so after right shift, the MSB will be the bit that is before them. I mean, if it is 1, the MS will be 1. If it is 0, the MS will be 0. Okay, just do the operations. You will get your answer. Step 1, it is 0 to 0. No operation, only a right shift. Now, students, please maintain these lines properly while writing, because this is the silly mistake that everyone does and then the answer became wrong. Please don't make Booth's algorithm complicated. It is very easy and you can teach it yourself. So 0, 0, 0, 0, do a right shift. 0, 0, 0, 0, 0, 1, 1, this 0 will come to here. And what will be in this MSB? Right, as it is 0, it will be also 0. So step 1 gives us this answer. Step 2, 0 to 1. When it is 0 to 1, we have to subtract m. Write this. Sub m, then do a right shift. See, I think I've already told you that if we write a minus m, it is equivalent to a plus m's 2's complement, right? I mean, if we write 8 minus 5, or we can say 8 plus 5's 2's complement. Plus 5's 2's complement is equivalent to minus 5. I've made an entire video on this, guys, so please check it out if you have not watched it yet. Only then your Booth's algorithm concepts will be clear, otherwise not. So a plus m, sorry, a minus m, or a plus m's 2's complement is same. So subtract m. What we have to do? The accumulator minus multiplicand. We know that I'm sorry that I have to change this page here. That is why it is a little bit tricky right now. Please write them before you perform your multiplication. A minus the multiplicand is 4. So a minus 4, I have to do this, but I can do a plus m's 2's complement. 0 0 0 0 plus 4's 2's complement is minus 4, that is 1 1 0 0. Okay, write down 1 1 0 0 0 0 1 1. Then do right shift 1 1 0 0 0 0 1, then 1. As it is 1, the ms will be also 1. Right? After step 2, we get this answer. Step 3, it is 1 to 1. When it is 1 to 1, no operations will get performed, only a right shift. So it is 1 1 1 0 0 0 0, then 1, and there will be 1. Step 3, it is 1 to 0. Okay, now get to remember, when it is 1 to 0, it is add m. Okay, right? Sorry, step 4. Add m. Then do a right shift. 1 1 1 1. M is 0 1 0 0. 1 1 1 1 0 1 0. This is the carry. So after this right bit on the right shift, 0 0 1 1 0 0 0. There will be a 0. As it is the 0 here, we will have another 0 there. So our final answer is the accumulator and the multiplier both, the both combination. This 8-bit register is our final answer, that is 0 0 0 1 1 0 0 0. And what is 24? 0 0 0 1 1 0 0 0. The answers are similar, right guys? So the both algorithm is exactly right, and we can perform a multiplication in this way. Okay, 4 cross is equal to 24. This is the answer. Now I think we know that we are performing Booth's algorithm because of the negative number algorithms, right? We can't perform sign numbers here, so that is why we are doing. So let us give an example. 5 into 7, sorry, minus 7. 5 into minus 7 should give you minus 35. Just do this with me, please, I'm begging you. Plus 5 equals to 0 1 0 1. Minus 5, it will be 1 0 1 1. See, these are the basic steps that you need to follow. If you do them correct, if you do them in a correct way, only then your whole answer will get correct, and you can score plus 10 on 10 on your exams, and it will make me tremendously happy. Please do this. It means a lot when you guys do well. Okay, 0 1 minus 35. Okay, do this. First, accumulator, which is initialized with 0 1 0 0 0. 0 0 0 0, the 4 zeros. Then multiplier, the Q, minus 7, it is 1 0 0 1. Then the imaginary 0. Then the multiplicand. I have to tell you something, maybe I missed it. Multiplicand, multiplier, accumulator. What is this? This is the imaginary 0 that we need to have if we want to perform Booth's algorithm. This is not present inside the computer. We have to assume in this algorithm so that it can be performed in a accurate manner. So just do this. it's a 4-bit multiplier. We need 4 steps. Just make some lines. 0, 2, 3, 4. Step 1. 0 to 1. Okay. 0 to 1. It means subtract m, then do a right shift. Subtract m, a minus m or a plus m's 2's complement. M is plus 5. So plus 5's 2's complement minus 5 means 1 0 1 1. Just do this. 1 0 1 1 plus 1 0 1 1. Then do the right shift. 1 0 1 1 1 0 0. That 1 will come here, and as it is 1, so MSB will be so 1. After the first step, we will get this answer. Now step 2. It is 1 to 0. So what you have to do is add m. 1 to 0, add m, then do a right shift. 1 1 0 1 plus 0 1 0 1. So the answer is 1 1 0 carry 1 1 1 0 carry 1 1 1 0 carry 1. After the right shift, it will be 0 0 1 0 1 1 0. Then it's a 0. As it is a 0, the answer will be 0 0 0 1 0 1 1 0, and there is a 0. Step 3. 0 to 0. No operations, only right shifts. So this was the answer. So now in the next step, 0 0 0 1 0 1 1 0. As it is 0, we have to put 0 here. This is our answer. Step 4. It is 0 to 1. When it is 0 to 1, what do you have to do? 0 to 1. Subtract m and then do a right shift. Subtract m or just add the 2's complement. 0 0 0 0. 2's complement is 1 0 1 1. Right? 1 0 1 1. 1 1 0 1. After the right shift, it will be 1 0 1 1 1 0 1. This 1 will come here, and as it is a 1, so this will be the 1. This is our final answer. The multi-accumulator and the multiplier, both of them will combine into one answer, that is 1101 1101. Now we know minus 35 is 1101 1101. Correct? Both the answers are equal. So you can do this in sign multiplications also. I know this is a really long video, but this is really important for your exams. This is how Booth's algorithm is performed. So just repeat this again with me, and remember this chart very carefully. Step 1. Check the imaginary 0 with the LSB of multiplier. 0 to 1. 0 to 1, then subtract m. 1 to 0, add m. 1 to 1 or 0 to 0, no operations, just do right shift. 0 to 1, okay. Then subtract m. We have done subtract, then just do a right shift. In this vacuum place, the MSB will be the same as the previous one, and so the next one 1, so you have to press 1 also. Do the steps as many times as there is a bits in multiplier. So there is a 4 bits multiplier, so you have taken 4 steps. Each step just do some operations, then right shift, and at the end you will get your final answer. This is how Booth's algorithm is performed, and please do this very carefully. This is a very important question. It comes in exams all the time. So if you had any queries related to this video, please ask me in the comment section. I will try to answer them all. And all the best for your exams. Thank you for watching.